everyone, welcome into lecture number 3 on linear equations. Let's start with a definition. So a linear equation, a linear differential equation is going to be the following. Let's say it this way. So a first order differential equation. These are what I call FODE, F-O-D-E. So I usually don't write all this out, right? But F-O-D-E, an F-O-D-E or a first order differential equation is said to be linear if, and this is what we're defining, right? Linear if and only if it can be written in the form, right, in the form of the following. And so the following, this is the linear form right here, that dy by dt, the first derivative, plus some function of t times y equals some function of t. All right, and so we talked about this in the first lecture in our classification, but this is again, this is the general form for a linear equation, first order linear equation. This could be written sometimes, you'll see this as y prime, all right, and this one is y. And the whole idea here is that the y prime and the y are not mixed up in any functions themselves. They can be multiplied by functions of t, but they can't be multiplied by each other, and they can't be inside of any other functions in any other way. And then the equation can equal some function of t over here. Now, because of this g of t right here, these equations are generally not separable. So that's the end of our definition, but in general, linear equations are not separable. So the techniques that we learned in the last lecture will not apply, at least not apply directly. But it turns out that there are ways to make this equation separable, or at least to take advantage of some parts of it that are separable. So we're going to derive a solution for this equation, for this general equation, one way, and then do some examples, and at the end we'll talk about a different way, a second way to derive the general solution to a linear equation. All right, so let's get right into it. So this item number 2 here is going to be the derivation of the general solution. All right, and what we're going to do is we are going to observe that, again, we've already observed that it's not separable, but we're going to try to make this into a separable equation. All right, so let me write it this way. I'm going to rewrite this as y prime, just for the sake of almost laziness, just so it's easier to write down. But y prime plus p of t times y equals g of t. Again, it's not separable. All right, we would like to make it separable. So this is our goal, kind of in an ideal world. So can we make this separable? And of course, when we try to make this separable, we have to do so in a way that does not change the answer, right? Because then that would not be legal. So whatever we do to this equation, we have to try to make sure that we do it in a way that doesn't change the equation at all. And as you might remember from an algebra or calculus course, we can multiply an equation by any non-zero constant, and it won't change the answer to the equation, right? The solution of the equation. We can even go further, right? We can multiply this by a non-zero function, or let's even say a positive function of t in this case, and it will not change the answer. All right, so here's what we're going to do. We're going to multiply the entire equation by a positive function, which we're going to call mu, and mu is just a function of t. All right, so this is a Greek letter mu. All right, let's see what happens when we do this. If we have to multiply all the parts, right? So we're going to take, and I'll just write it right here, but we're going to multiply the whole equation by mu. That mu's got to distribute to everything, right? So it's going to end up giving us mu times y prime plus mu times p. I'm going to leave off the t, so everything here is a function of t, right, times y. And on this side, it's going to equal mu times g. All right? And at this point, we would really like this left-hand side to just be so everything on the right-hand side is a function of t, right? So we would really like this to be the derivative of some function that we can write down. And we notice that this term, so notice that this term right here, and then part of this term, it looks kind of like this could be a product rule, right? We have a y prime plus something times y. So something times y prime plus something times y. All right, so let's notice the following thing. If we were to take the derivative with respect to t of mu times y, this function, this positive function times y, then, and we apply the product rule, then usually the derivative hits the first one and then the second. But I'm going to do it in the opposite order, so it looks like this, right? I'm going to leave the mu alone. The derivative hits the y. Plus, the next step is that the derivative has to hit the mu, right, and leave the y alone. All right? This would be really nice because this is the derivative of a function. What we do now is we just compare, right? So we compare what we have here to what we have up here. We want to compare these. It would be nice if they were the same. So I should rephrase this. We want to choose the mu so that these are the same. We want to choose mu so that they are the same. And we notice that these terms are exactly the same, right? Mu times y prime. Those are exactly the same. Over here, the y is the same, right? And so in order for these two to be equal, then we need to find a function mu for which those two are equal, right? So such that mu prime equals mu times p. So that becomes our new goal, all right? So in other words, this original goal that we had will be satisfied. We'll achieve that goal if we can find a mu that satisfies this relationship. So let me write it this way. For this relationship to be satisfied, then mu prime, this derivative, has to equal mu times p, right? And remember that everything here is a function of t, so d mu by dt has to equal mu times p of t, right? Remember, p is a function of t. And this is the kind of equation, this is separable, right? So this is the kind of equation that we've studied from the very beginning, even from lecture 1. But this one is separable. So that's good news, right? It's good news because we know how to solve the separable equations. So what do? We divide by mu, multiply over the dt, and we get this equation. So 1 over mu d mu is equal to this function p of t dt. We can just integrate both sides, all right? And we end up with natural log of the absolute value of mu is equal to this integral. We don't know what the p is general here, right? So hopefully we'll be able to compute this in general, but for right now it's just integral of p dt, right? And so then we want to solve for mu. By the way, there's plus c here, but we just need any mu. We need any mu. So I'll put the c, but we just need any mu that's going to satisfy this relationship. And so we have to exponentiate, right? So mu is going to equal e to the integral of p dt. Just going to write it this way. And again, I'm going to choose the c to be 0 because we can choose any c that we want right here. All right, so this function right here, this is called the integrating factor. Integrating factor. And you're going to need this, right? So we're going to need to know this formula because we're not going to want to redo this derivation every single time. So it turns out that now this is the formula for mu. That formula for mu comes from the original equation. It comes from this function p, right? As long as it's in this original form, then that function p plays a role in determining the function mu. Now that we have mu, then these two things that I've underlined in blue here are now equal, right? So once we have our mu, we can rewrite this equation. So all of that work was to just be able to transform this into this following equation, what I'm going to write. So now the equation becomes d by dt of mu times y, where this is mu. I'm going to keep writing mu, but this is the formula for mu, right? Mu times y equals mu times g. And again, this is mu, right? So mu times g. And at this point, this is separable as well, because what we can do is we can just take this dt, multiply to this side, all right? And our equation becomes the differential of the product function, mu times y, equals mu times g dt, also a differential, right? So this has been separated. And now when we call in our integral and integrate both sides, the integral and the differential, those are just going to cancel, right? And so this is going to leave us on the left-hand side with mu times y. And on the right-hand side, again, we don't know right now these are just symbolic functions, right? But so this is just going to be integral mu times g dt, and we can put our plus c here. We can just work that in. But remember, our goal is to find this y, right? Find this function y. And so we just have to divide through by mu. And by the way, I should have verified that this function, at this point I should have done it, but it worked out, right? But this function is always positive because it's an exponential of some other function. So there's no way that this function can be 0, right? E to a power can never be 0, and it can also never be negative. So this function is purely positive, and so it satisfies our criteria up here, right? And what that also means is that at this point we can divide through by mu, right? And so we arrive at our general solution. So I'm going to divide through by mu, but I'm going to write some words here first. So here is the punchline, right? The general solution of the linear, first order, right? Linear differential equation So the equation was given to us as y prime plus p of t times y equals g of t. So the general solution is that y of t is equal to 1 over mu of t times the integral of mu of t times g of t dt plus constant over mu of t. All right, and so this is great, but we have to remind ourselves what mu is, right? So mu of t, this is our integrating factor, is the exponential function e to the power p of t dt. All right, so this is the key. So from here, all we have to do is use this information, right? Use this information to first identify that our equation is linear and it's in this form, then find the integrating factor, this mu, and then use the integrating factor to plug into the general solution. So we don't have to go through the entire setup that I've just gone through. We just have to jump straight to this step. As long as we can identify that our equation is linear, then we can go from here. Okay, so let's do some examples now. The first one is going to be the following. So this is number 3. Item number 3. So this is our example. We want to try to solve this equation. So this one is going to be 4 plus t squared times y prime plus 2ty equals 4t. All right, and so again, this lecture is on linear equations, so we would hope that this is linear. And by looking at, based on our definition of linear from lecture 1, the classification lecture, it is linear because the y prime and the y are not mixed up in any functions themselves. But it's not exactly in this form, right? It's not exactly in this form because the coefficient function on the y prime should just be a 1, and it's not. So the first step to this one is to divide through by this 4 plus t squared and just rewrite it. That's not going to change this at all because actually this is a positive function, right? So sometimes you'll get a restriction on your domain of your solution at this step, but in this case we don't, right? So y prime plus, and then we just multiply through. So this becomes 2t over 4 plus t squared times y equals 4t over 4 plus t squared. Okay, so at this point I'd like you guys to take a moment and try to solve this equation. So now it's in the right form. You can see this right here. These are the things you want to work out. Identify p, identify g, and then work out the general solution here. And I'll check back in when you're done. All right, so now that you've had a chance to do this one on your own, let's do it together. So the first step is to identify the parts, right? The major players in this formula. So this is our P. So there we go. I'll get it so we can see everything here. There's our P. And then this is going to be our function G. And then we know the roles that these things play, right? Whoops. So there's the roles that these play. Okay, so we need to then write this all out. So if this is our function P, then we need to integrate this and exponentiate it, right? So the integral of p of t dt, this is going to be the integral of 2t over 4 plus t squared dt. This one can be done by a u sub, right? But the derivative of the bottom is 2t. That's exactly what we have up here. And so this is just going to be a natural log, right? So the natural log of 4 plus t squared. And then remember, this is not our function mu yet. We still need to exponentiate this. All right, so this means that our function mu is e to this power of this function, 4 plus t squared. And of course, this just leaves us with 4 plus t squared. Okay, so this is our, actually in this case, our integrating factor is this 4 plus t squared. So that's going to be our mu. It shows up here. So again, if we highlight, if we highlight, the mu is going to show up in all these spots. In 2 of them, that's just the answer, and it's in the denominator. But this has to also get mixed in or multiplied by the g to solve the integral for the general solution. So let's do that part now. All right, so our general solution, so our integral of mu times g dt, this is going to become the integral of 4 plus t squared times, on this side, 4t over 4 plus t squared, right? 4t over 4 plus t squared, use this one, dt, and then we see this is pretty nice, right? Those are going to cancel in this example. That doesn't always happen, but this is a nice one to start with. And this then leaves us with 2t squared. All right, and remember, the plus c is already built into the integral the way that we've done it here. So the plus c is going to already be taken care of. This right here is then the answer to this integral portion. And so our general solution, so the general solution is now given by this formula. So y of t is equal to 1 over mu, so 1 over 4 plus t squared times the integral, which was 2t squared, plus constant over mu. Just going to write mu there, over mu, which is 4 plus t squared. And so this can all be combined in this case, right, to be just 2t squared plus c over 4 plus t squared. All right, and so this is equal to y. This is our solution, our general solution of that first linear equation example right here. Okay, let's try another one. This one's going to be an initial value problem. So there are different ways to organize your work, and this one I wrote out all the different parts and then put them together at the end. Sometimes it's useful to just write out the general solution and then work out the pieces, you know, as one whole piece, and then you don't have to remember to put it back together. It's kind of up to you, but as long as you do the final step of getting everything put back together into the final stages, right? So here's the next example. Let's solve the equation y prime plus 2y equals t e to the minus 2t. This one's going to be an initial value problem. So here y of 1 equals 0. All right. So take a moment to work this one out, and I'll check back in with you in a minute. All right, now that you've had a chance to work this one out yourself, let's see if we can write the answer down. This one is already in the proper form. So this one is linear, right? It's y prime plus 2y, etc. It's got all the pieces that it needs. So in this case, let's write down our function p of t is just the coefficient function here. It's just 2. It's just 2, okay? So that's just 2. And so that means that our mu is equal to e to the integral of p dt, 2 dt. Well, that's going to be e to the 2t. All right, e to the 2t. And now that goes into, this goes into our general equation. So let's write the general equation now. So y of t is equal to 1 over mu. So, by the way, if this is mu, because of the way this is written, right, then this means that 1 over mu is equal to e to the minus 2t. We can just write it that way. so we don't need to write it as a fraction. And then the integral, we have our mu, so e to the 2t, and then we have our g, so t e to the minus 2t dt plus constant e to the minus 2t. All right. At this point, we see that we get some nice canceling again in this one, right? So that's going to cancel, and then we get our answer here. Y of t is going to be equal to e to the minus 2t times the integral of t dt. So that's 1/2 t squared, right? Plus constant e to the minus 2t. But this is an initial value problem. So now we need to plug in the initial condition, which was y of 1 equals 0. So this says that y should be 0 when t is 1, right? So when t is 1, y should be 0. So we plug in, on one hand, this should be 0. On the other hand, it's equal to y of 1, right? So we plug in 1 for t. So this is e to the minus 2 times 1/2 times 1 squared plus c e to the minus 2, right? And this is supposed to equal 0. So c then has to be, so this is 1/2 of e to the minus 2 plus something e to the minus, so this has to be minus 1/2, right? So this tells us that our c should equal minus 1/2. And then our particular solution, remember, when you solve an initial value problem, you get a particular solution. So remember, this is called the general solution, but that's not the solution of the initial value problem. The particular solution of the initial value problem is now y equals, we can write it this way, 1/2 t squared e to the minus 2t minus 1/2 e to the minus 2t. And that's this one right here, right? You just plug in negative 1/2 for c. And so there's the solution to our initial value problem. All right, this next one, let's do it together. So this will be our last kind of concrete example. So far, the examples I've done, the integrating factor has made it so that the integral is very simple, right, to do. So in this case, in both cases, we just ended up having to integrate a linear term. It's very simple. That doesn't always happen. So here's an example of where that might not happen. This is item number 5, right? Yep. So for this one, we want to solve the initial value problem. 2y prime plus t times y equals 2. And the initial condition is that y of 0 is equal to 3. Okay, this is not quite in the right form, right? So the first thing we need to do is just divide by 2. It's very simple, but we have to do it, right? So y prime plus t over 2 times y is equal to just 1 now. And the initial condition stays the same, right? All right, so now that this is rewritten, what we want to do is then just identify the p. So our p function is t over 2. And this means then that our integrating factor mu is going to be equal to e to the power of the integral t over 2 dt. And we've integrated these linear terms a few times in this lecture already. So this leaves us with e to the 1/4 t squared plus c. But remember, we don't need this. We'll just take c equal to 0 for these. But now this becomes the integrating factor, right? And our g function is just 1. So that's going to be pretty nice. But what we end up with then is the general solution, or the solution is the following. So I'm going to write this out, and then we're going to kind of adjust it a little bit. But this one's going to be y equals 1 over mu. So remember, we can do that trick because it's still an exponential where we just change this sign to a minus, right? So e to the minus 1/4 t squared times the integral of mu times g. So that's e to the 1/4 t squared dt plus constant times mu, right? So plus c e to the minus 1/4 t squared. And when we look at this one now, we see that the integrand of the solution is a function that has no simple antiderivative. So there's no nice simple function antiderivative of this exponential function where the exponent is squared, right? E to the t squared has no simple antiderivative. And so we can't write down an antiderivative solution for this. What we can do instead is we can use the fundamental theorem to write this integral, right, as a function of t. And so we can write down our initial t value is 0, right? So we can use the fundamental theorem to write this as e to the minus 1/4 t squared times the integral from 0 to t, all right, times e to the positive 1/4, and now we need a different variable for integration, right? So I'm going to use s squared ds plus this term stays as it is, e to the minus 1/4 t squared. All right, and now we need to check our initial condition, right? So we still need to figure out what c is here. So when when t is 0, y should be 3. So we do the same kind of trick. When y is 3, when t is 0. So this is going to be e to the 0, integral from 0 to 0 of e to the 1/4 s squared ds plus c e to the 0. This one, the integral, is from 0 to 0. So this whole term right here is gone, right? So that's 0. And then this is a 1. And so this whole thing equals just c. So then we obtain from this that c should be 3. And so in this case, our particular solution, we are going to leave in terms of an integral, but we're going to use the fundamental theorem of calculus to make it a particular integral, right? So the particular solution to this initial value problem is that y is equal to e to the minus 1/4 t squared times the integral from 0 to t. This 0 comes from, this 0 comes from the initial t value, and then we had to solve for c using the initial y value. But integral of 0 to t of e to the 1/4 s squared ds. This could be any variable you want, but the point is that it's an integration variable. And then plus 3 e to the minus 1/4 t squared. So there's our particular solution. Now, this might feel like it's not a very great solution or whatever, but actually in practice this is perfectly fine. There's no problem here at all, because in practice we know from calculus 2 that there are many different numerical integration methods like trapezoidal rule and especially Simpson's rule that can help us compute this integral for any fixed value of t, right? So for any values of t that we need, we can just use numerical integration in practice to approximate the solution to a certain, whatever our threshold is. So we are actually very happy with this solution. This is okay. We consider this in math to be a very good solution. All right. It looks a little funny, but it's a perfectly fine solution. So now I'd like to show you another way to derive the solution of a linear equation. So this method is called the variation of parameters method. And this one we will use to solve more complicated equations later in the semester, but also it works pretty nicely for solving these first order linear equations. So let's recall that we have, let's say we have our first order linear equation. So we have our y prime plus p of t times y equals g of t. All right, and we said from the very beginning that if this function g of t is not 0, then this is not separable, right? So this is what we said from the beginning. So if g of t is not 0, then this is not separable. And so then we had to use the method that we derived at the beginning. Let's ask ourselves, though, what would happen if it is, right? What if g of t does equal 0 for all t? So in other words, what if it's just 0? Let's solve that one. So then we'd have y prime plus p of t times y equals 0. We can solve this, right? So this one is separable now because this becomes, this left-hand side, remember, means dy by dt. And if we move this over, it's negative p of t times y. And then this is separable, and we get 1 over y equals negative p of t dt. Integrate. This is going to look pretty familiar, but we integrate, then we get natural log of y equals over here. This is going to be, so this minus sign can just come out, right? So minus integral p of t dt. We don't know what p is, right? So we can't actually do the integral, but then plus c. And then when we exponentiate, we get our solution for y. So y is then equal to constant times e to the minus integral p of t dt. So this is the solution if g is equal to 0. Okay, if g is just equal to 0. Let's now think about this. So if g is not equal to 0, this is where the variation of parameters comes in. So if g of t is not equal to 0, then one way to try to find the solution of the equation where this is not a 0 is to assume that this constant is actually a function of t itself. All right? So if g of t is not equal to 0, then we guess, well, we're going to say we guess, but we're going to make this guess, right? We guess that the solution to this equation, y prime plus p of t times y equals g of t, is given by this. So y of t is going to equal, I'm going to swap out this constant with a function. All right, and I'm going to call that function u of t. All right, e to the, that's just to make sure that we can tell that that's a function now and not a constant. So I don't want to call it c because it's going to be a constant. And so we just swap out the constant c with a function u. And if this is really going to be a solution to this equation, then we should be able to take the derivative, plug it in, right? And everything should be equal. So that's going to give us criteria on this u. So now we just need to take the derivative. So that's our y, right? So this will go, this y will go into our differential equation, not there, right here, right? And then we need to take the derivative of this to go here. Okay, so that's the next step. Take the derivative of this new function y. So then y prime is equal to, so this is a product rule, right? So the product rule is first going to hit this. The derivative is going to hit this. We're going to get u prime of t times this. So times e to the minus integral p of t dt, plus then the u is going to be left alone. And the rest of this is going to, we have to take the derivative by chain rule, right? So the derivative is going to be the function itself. So e to the minus integral p of t dt times the derivative of the upstairs. So there's a minus, and then the derivative of the integral is just going to be p. Okay, so all of this becomes the y prime. And then we plug this all back into the equation. So this goes in for y. All of this goes in for y prime. And then we'll see if we can solve for u in terms of g. So at this point, we have the following. U prime e to the minus integral p dt plus, this one is negative actually, right? So that's going to be minus u times p times e to the negative integral p dt, and then plus p times y. Y is u e to the minus integral p dt, and then we just have g over here. All right, so I've left off the of t's in the functions, but we know that they're there. And then look at these two terms are the same, right? The order here doesn't matter, so those cancel. And we are left with this equation then, that u prime e to the minus integral p dt is equal to g. Again, this is a positive function, so we can divide it through, or we can multiply through by the one, the integral, or the e to the positive integral p dt, and we get du by dt is equal to e to the integral p of t dt times g. All right, and then separate, integrate, and look what we get for u. It shouldn't be too much of a surprise, right? U is going to be the integral of e, the integral p dt times g of t dt, plus a constant, right? Plus c. Okay, so at this point, we now remember what was the point of the u. Well, we go back up here, and our u was the coefficient here on this function. So everything here to make this back into y has to be multiplied by e to the minus integral p dt. So this means then the general solution of the original linear equation is now y of t equals u times that e to the minus integral p dt, right? So I'm going to write this. I mean, I think it's pretty clear at this point what everything is, right? Remember, e to the integral p dt is at what we've called mu, and then this one is 1 over mu. But let's write it out. So e to the minus integral p dt times the integral of e to the integral p dt times g dt plus c e to the minus integral p dt. All right? And so this is another way to get to the same equation because, again, if you write mu is equal to e to the integral p dt, then this is exactly the same. Exactly the same solution. All right, it's not even like in a different form. It's exactly the same. It's just a different way of getting at the same solution, okay? So like I said, this is called the method of variation of parameters. And we'll see this again later in the semester. The major idea here is that we have varied the constant, right? So that's the parameter in this case. Varied the constant, the unknown constant, and thought of it as a function. And notice we still got an unknown constant out because we integrated. We got another integration variable, right? Okay, so I'll leave this one here, and I'll see you guys in the next one.